Hello everyone, I am Rahul Mandal, third year undergraduate student from Computer Science and Engineering department from dual degree course. So today we are going to present our Artificial Intelligence Foundation and Application course group project. So the topic we have chosen is Artificial Intelligence in Medical Imaging. So these are our group members, myself Rahul Mandal, second is Chukka Jashwant Kumar, third is Suraj, fourth is Pagoti Yashwant Krishna. This is the table of contents, the subtopics which we will be covering in the presentation. So, introduction. So, as we all know, that prevention is better than cure. Accurate and early diagnosis and prognosis is very essential to prevent any serious condition to develop further. So, what is medical imaging? So, medical imaging, also known as the radiology, is the field of medicine in which the medical professionals recreate various images of parts of the body which help to diagnose, monitor, or to treat medical conditions. So, medical imaging deals with the interaction of all forms of radiations with the tissue and the design of technical systems to extract clinically relevant information, which is then represented in image format. So, medical images range from the simplest, such as chest x ray, to sophisticated images displaying temporal phenomena such as the functional magnetic resonance imaging. So, why medical imaging? So the question is how medical imaging helps. So basically, medical imaging plays an important role in modern medicine. Artificial intelligence helps us to get the visualization of human body and examine the human body in depth, which manifests structures inside our body in great detail. So medical devices nowadays are getting much smarter with more precision and cost efficient to provide seamless experience for end user. So the recent boost in field of artificial intelligence, more effective solutions came to light to solve in countless problems using deep learning and machine learning algorithms. So why do we choose AI in healthcare? So healthcare, as we know, is one of the most important and the critical sector in broader landscape of big data because of its fundamental role in productive, thriving society. So here are some of the examples of how AI can help in healthcare. So AI can help doctors, nurses, and other healthcare workers in their daily work, and AI can also help in help improvement of the preventive care and quality of life, provides accurate diagnosis, etc. AI can also play a crucial role in global health as a tool for combating epidemics and pandemics. AI can also predict and track the spread of infectious disease. So basically, when artificial intelligence applied to medical images allows us to automate disease detection and to get organized history, stage or subtype, and patent classification according to therapy outcome or prognosis. In recent years, an unprecedented amount of digital imaging data has become available in medicine thanks to the digitalization, affordable data storage, and improved imaging techniques. This leads to an unprecedented interest in applications of artificial intelligence to images, which has boosted research efforts of medical physicists. Thank you.
My name is Suraj Gupta, and now I'm going to talk on the challenges to overcome for AI to thrive in medical imaging. While AI guided diagnostics in cancer screening programs are already demonstrating huge progress, the field needs to overcome further regulatory, ethical, and technical challenges to realize its full potential. Here are four key challenges that need to be overcome for the use of AI in medical image to thrive. The first one is patient acceptance. Education about AI and its positive impact on care is vital for patients to accept its involvement in their diagnosis. In my view, it is the responsibility of healthcare providers to communicate this in collaboration with clinicians. For example, educating patients around how AI guided diagnostics has the potential to deliver greater accuracy of results and the potential to speed up diagnosis and ultimately the treatment. These types of outcomes presented simply are crucial for patients to understand in order to recognize AI's part in medical diagnosis. The second one is clinical confidence. Working in collaboration with radiologists, pathologists, and cytotechnologists will be key to improving confidence in AI's medical image analysis capabilities. Clinicians play a crucial role in sourcing unusual cases so that algorithm constantly evolves. In return, clinicians become more confident in the results that AI provides them. In minutes, the AI algorithm can identify a small number of abnormal cells. This gives the clinicians confidence to work side by side with the system. The third one is regulatory clarity. Experts in digital pathology, doctors, and AI specialists all agree we need greater clarity and consensus from governments worldwide to decide on a regulatory approach to AI. There are already some CE marked algorithms for use in medical imaging, such as breast cancer and prostate cancer, that assist with prioritization and risk stratification. This is a positive step, but we still need further consensus. The fourth one is a safeguarding framework. It is a reality that humans make mistakes in diagnosis, but we also need to consider what happens when AI is involved in misdiagnosis and navigate questions of accountability. We require a multidisciplinary task force to work through these type of questions to build a more holistic approach to safeguard AI systems. What next for AI in medical imaging? When these four areas that I mentioned above are tackled in depth, we will see wider adoption of AI-driven diagnostics, leading to even higher standards of diagnosis and care for patients and earlier detection. It is these type of innovation that spur on our research, knowing we have potential to save more lives. So let us discuss the recent advances in the same field. Last month itself, technology company NVIDIA unveiled the NVIDIA Clara platform, which is a combination of software and hardware working together to bring AI to future medical instruments. The Clara software development kit will enable developers to apply a wide range of AI-powered applications to existing medical imaging equipment. NVIDIA may be stepping up its game in the world of medical AI, but the company is certainly not alone in its endeavors. Here are four new devices featuring AI-powered medical imaging tech. The first one is CT scanners. Earlier this year, deep learning startup Adoc revealed what it referred to as the world's first comprehensive full body technology that can use AI to analyze computed tomography, that is CT scans. ADOC's AI-powered medical imaging technology can highlight any abnormal findings on a patient's medical scan so that they can be reviewed by radiologists. Further moving MRI machines. Deep learning company Subtle Medical is a member of NVIDIA Inception virtual accelerator program and is aiming to create MRI machines that acquire images in a quarter of the time while requiring just 10% of the contrast dosage to patients. The third one is optical coherence tomography. Google's DeepMind recently developed an AI system that can quickly detect over 50 eye disorders using routine medical scans. Optical coherence tomography, that is OCT, relies on coherent light to capture micrometer resolution 2D and 3D images from within optical scattering media. The fourth one is ultrasound that we all have heard of. GE Healthcare introduced a new medical imaging tech in March in the form of Logic E10 radiology ultrasound system, which is aided by AI to quickly capture data and reconstruct images. The digital system employs closed connectivity and advanced algorithms to ensure 48 times more data throughput and 10 times processing power of previous system. Further, I would like to discuss on the AI marketplaces that are becoming platform oriented. The ones that are in front of these is Google, Apple, IBM, and Microsoft, who show intense fascination with AI-helped medical imaging. A few examples of the same are that Google collaborated with Zebra Medical Imaging, Change Healthcare, and Cantron Systems, organizations associated with AI utilization in clinical imaging. Google also offers Google Cloud for information stockpiling and ML improvement stage to many accomplices. Further, Microsoft's AI platform made interest in its stage for designers with the end goal of further developing clinical imaging diagnosis. Not only Google and Microsoft, but Amazon also offers an AI based health that quickly distinguishes medical images.
Hello everyone, I'm Yashwant Krishna, a third year undergraduate student of the Department of Computer Science and Engineering. Current role of AI in medical imaging. In today's world, AI has come a long way. They have become effective and efficient at identifying diseases than human experts. AI algorithms that are deployed today are used to analyze data that help the doctors to medically diagnose patients. As AI evolves and becomes more sophisticated, and being the broadest category, it encompasses specific subsets like machine learning, which itself has more specific subfields like deep learning. Let's take a look at the role of deep learning in medical imaging. Deep learning algorithms that are applicable in radiology are called convolutional neural networks, which takes an input image, assign weights to various aspects or objects in the image, extracts the features until the desired task is reached. Applications of DL in medical imaging include object detection, object segmentation, and object classification. Let's look at these applications in detail. Object detection is used to locate a lesion, which is a region in an organ or tissue which has suffered damage through injury or disease. White matter hyperintensities, lunar stroke lesions indicate risks for stroke and vascular dementia, which is a condition caused by the lack of blood that carries oxygen and nutrients to a part of the brain. And then comes object segmentation, which is used for lesion contouring. Here's an image of MRI based contouring of the lesion using different radiotherapies. Object classification, which is used to differentiate between malignant and benign lesions. Let's take a look at the role of machine learning in medical imaging. Machine learning is a field of study that gives computers the capability to learn without being explicitly programmed. Machine learning algorithms pick 80% of the data from the dataset randomly, trains it, and uses it to predict the results of the remaining 20% of the data. One of the use cases of machine learning algorithms in medical imaging are to separate brain tumor from normal brain tissue. This is done as follows. Let's say we have a model with 4 features, first two being mean CT attenuations of the region of interest on the non-contrast and contrast material enhanced images respectively, third one being the variation in attenuation, and the fourth one being the tubularity of the voxels. Generally, in the CT scan, brain tumor tissues along with the blood vessels get enhanced, and to eliminate the vessels, we calculate the fourth feature, which is the tubularity of the voxels. After calculating all the 4 features, we randomly select 80% of the data and add random weights to each of these 4 features and add the 4 products. If the sum is 0, the algorithm declares the region of interest as tumor, or else it's a normal brain tissue. Weights are adjusted until the accuracy cannot be improved. Using the training data, the algorithms predict the output of the testing data and uses it to calculate the accuracy of the predictions with the true data. Overview of an AI pipeline. There are 5 stages in the pipeline, and the first stage is acquiring the image itself. As the doctors have access to the real time patient data, different scans and clinical trials are done on the patients and the images are obtained. The images obtained are not in the right format, and pre processing has to be done and convert them into different formats to make them compatible to be used by the machine learning and deep learning algorithms. These algorithms perform model training and validation on the provided dataset. The next stage is prediction and analysis of the data, where the algorithm predicts whether the brain contains tumor cells or not, if the patient is going to survive or not, etc. Finally, model deployment. Once the testing is done successfully and after getting legal approvals for the algorithm to be used, it can be implemented in real time. Let's take a look at the few applications of AI in medical imaging. AI can detect pneumonia, which is an infection of the air sacs in the lungs, pneumothorax, condition of a collapsed lung, and many more. It can also detect breast cancer with 99% accuracy and can also detect left atrial enlargement from chest x-rays.
My name is Jashwant Kumar. Now I'm going to discuss on the topic of the future of AI in medical imaging. Till now we have discussed what is medical imaging, the challenges faced, and the advances in the field of medical imaging, the role of AI in medical imaging, and even few applications of AI in medical imaging. So the next topic is the future of AI in medical imaging. From the early days of X-ray imaging in the 1890s to more recent advances in CT, MRI, and PET scanning, medical imaging continues to be a pillar of medical treatment. Current advances in the imaging hardware in terms of quality, sensitivity, and resolution enable the discrimination of minute differences in tissue densities. Such differences are in some cases difficult to recognize by a trained eye and even by some traditional AI methods used in the clinic. So, moreover, in the contrast to these traditional methods based on predefined features, we find that deep learning algorithms scale with data. That is, as more data is generated every day, and with ongoing research efforts, we expect to see relative improvements in performance. All these advances promise an increased accuracy and reduction in the number of routine tasks that exhaust time and effort. Despite the clear progress in the application of AI to medical imaging and the considerable investments being made in the companies and technology that support it, radiologists are slow to adopt AI in their work. Why is this happening? Only 56% of the radiologists they are currently using some sort of AI, and just 20 to 38% reported exposure to any of some these common use cases. It might be tagging images to ensure those for critical patients are reviewed first, or optimizing workflow for overall productivity, or automating part of the image analysis, or providing clinicians with decision support, or enhancing image quality. And finally, only 10% of very familiar with any of these applications. By this, we can conclude that many radiologists have some level of familiarity with artificial intelligence development, but very few are actively involved in it. This slide shows the survey results that respondents expect image quality enhancement for all these five use cases discussed here. It's the survey for all these five cases uh, given based on the values. So the next comes is like what is preventing AI adoption today? The biggest barrier identified was the radiologists themselves. 16% of them fear that AI has the potential to replace them in their traditional roles. However, many express skepticism in their current diagnostic capabilities of AI, particularly with respect to more complex patients or disease states. The second biggest barrier identified was the lack of regularity approval. 32% of the respondents saw this as the main impediment. Finally, uh, this is the cited from the journal from an American College of Radiology on the topic of an intelligent future for medical imaging, a market outlook on the AI for medical imaging. So, how the AI market will develop? The from this survey responses, we get clues as how the future market for AI will unfold. We would see three different stages of development of market in the AI medical imaging. In today's market, there are three different horizons here: Horizon 1, Horizon 2, and Horizon 3. In today's market, in Horizon 1, there are dozens of companies that offer AI applications for medical imaging, although none of them do at a scale. This fragmentation impedes market development. A comprehensive solution which addresses multiple modalities in multiple subspecialties and increase efficiencies like faster scanning. But this is not currently offered. Additionally, this fragmentation of the market makes it difficult for health systems and physicians to differentiate and select solutions. So here comes the Horizon 2. In Horizon 2, investments in AI-related medical imaging will still be growing fast, but a few companies will begin to emerge as leaders, differentiating themselves from the competition with more accurate and often comprehensive solutions and winning significant market share. There may be large incubated diagnostic companies, digital technology giants, or some large healthcare providers, or some unknown players. And coming to the Horizon 3, by the third horizon, the market for AI medical imaging will be stable and adoption will have grown exponentially. Some smaller companies will have formed partnerships with larger ones or have been acquired. Others will have
fallen by the wayside. In their place, established players will offer solutions across therapeutic areas, either on proprietary platforms that interact primarily with devices or systems within their own ecosystems, or on an open source platform that interact across all the devices and systems. Finally, here comes the conclusion part. AI is said to have a big impact on the medical imaging market and how radiologists work, helping them to speed up scan time, make more accurate diagnoses, and ease their workload. Despite the investments, AI solutions have not been adopted at scale in medical imaging. They need to be improved a lot. And I even tell that AI cannot replace radiologists. However, it can just facilitate everyday tasks performed by radiologists. As a result, early adopters of AI will likely be at the forefront of the radiology field in the future. While artificial intelligence can absolutely play a part in each of the steps in the diagnostic workflow and even replace a human in some of the parts like scheduling or some other parts, but it simply cannot replace a radiologist entirely. AI has helped radiologists prioritize patients based on the severity of the cases, improving patient safety and healthcare providers' efficiency. Even AI likely to gain ground quickly in the CT scan and enhancement of the imaging quality. AI techniques can be used at every stage of CT examination to benefit the quality of the resulting images, make the workflow more efficient for the operator and both radiologist, and reduce image noise such that the radiation dose applied to the patient can be reduced during the data acquisition so that the patient is healthy. In future, AI will continue to evolve and will be widely used as an assistive technology to perform tasks with more accuracy and efficiency with humans in the loop to make final decisions. Thank you for giving this opportunity.